Hello my friends, my name is Marcos Sarris, I'm CEO of GoLedger, a company that specializes on blockchain development. In today's video, we will be exploring some of the fundamental concepts behind Ethereum. Our primary focus will be on private blockchain networks built using Ethereum technology. We'll break down some of the key components that make Ethereum technology so unique, giving you a clear understanding of the core aspects of this groundbreaking blockchain technology. Ethereum technology was originally designed by the visionary Vitalik Buterin. While it was derived from Bitcoin, Ethereum introduced several groundbreaking changes. At its core, Ethereum registers a series of transactions on its blockchain. These transactions can involve either the transfers of Ether or the executions of smart contracts. What makes Ethereum unique is that each network can operate with own consensus mechanism. For example, Ethereum mainnet initially used proof of work, but has since transitioned to proof of stake to enhance efficiency and sustainability. In this presentation, however, we will focus on the KBFT consensus mechanism, a specialized protocol designed for private Ethereum networks. Ethereum accounts are a fundamental part of the network, and they come in two types: externally owned accounts, or EOAs, and contract accounts. EOAs are identified by a unit number generated as a hash of the public key, and they are controlled by private keys. They are primarily used to sign transactions, whether for transferred Ether or interacting with smart contracts on the blockchain. Contract accounts, on the other hand, are controlled by the code written within their smart contracts. Unlike EOAs, they don't have private keys. Instead, they respond to transactions sent and signed by EOAs. Basically, EOAs initiate actions, while contract accounts execute the logic programming them. This dynamic interaction forms the backbone of Ethereum's smart contract functionality. Now we are going to talk about the Ethereum nodes that are vital components of the networks responsible for validating transactions and maintaining the blockchain ledger. From a transaction flow perspective, these nodes are divided in two main categories based on their roles: execution clients and consensus clients. Execution clients manage the execution layer of Ethereum. Their responsibilities include executing transactions, updating the world state, and facilitating communications with other nodes in the peer-to-peer network. Consensus clients operate in the consensus layer. They handle attestations and validation votes to determine the next valid block in the blockchain. This process ensures that the entire network reached agreement on the blockchain current state. When using the KBFT consensus mechanisms in a private network, it is perfectly fine to run a Bezel client that fulfills both roles, managing both execution and consensus. This differs from the Ethereum mainnet, which typically requires a dedicated client, such as Teku, for validation purposes. Now, depending on how a node handles storage, it is categorized into different types. First, we have full nodes, which store the entire blockchain along with all transactions and smart contract bytecodes. They ensure the integrity, reliability, and decentralization of the network. Next, we have the light nodes that, unlike full nodes, they store only block headers instead of the entire blockchain. They depend on full nodes for transaction verification, making them ideal for devices with limited storage and computational power. Lastly, we have archive nodes. These nodes store not just the entire blockchain, but also maintain all historical states and transactions. This makes them perfect for applications that require access to past blockchain states. Each type of nodes play a vital role in maintaining and scaling the Ethereum ecosystem. Each block registered in a private Ethereum network has a specific architecture, which basically consists of three main parts: the header, a list of transactions, and a list of transaction receipts. The first part is the header, that includes essential metadata about the block, and it contains the block number, the timestamp of the block, and block hashes, along with patrician-Merkle roots, which represent the blockchain current state. These roots ensure the integrity and security of the data, and we'll talk about them later in this presentation. Next, we have the transaction. Each transaction can be from a simple cryptocurrency transfer to a contract deployment, or a smart contract execution with specific arguments. At the end, we have the transaction receipts. Each receipt provides a summary of what happened in each transaction, and it may include logs, events triggered during the transaction, and details about the gas consumed, helping track of the transaction computational cost. Configuring a private Ethereum network requires defining specific parameters to customize the blockchain according to your needs. At the heart of the network configuration is the Genesis block, which defines the starting point of our networks and contains essential settings. The chain ID serves as a unique identifier distinguishing your private network from others. For example, Ethereum's mainnet has a chain ID of 1. Next, we configure the consensus algorithm, which defines how the network reaches consensus on the blockchain state. You can choose from several mechanisms, such as KBFT or IBFT, both Byzantine fault tolerance algorithms that ensure fault tolerances and prevent tampering, or you can choose Proof of Authority, POA, which relies on trust validators to secure the network. The gas limit setting defines the maximum amount of computational work that can be included in a block, ensuring efficient and optimized network performance. Additionally, the max contract size setting limits the size of deploying smart contracts, enhancing storage and network efficiency. Furthermore, you can register pre-funded accounts in the Genesis block. For instance, a specific account might receive 2 Ether at the start of the private network, facilitating the initial operations. These and other configurations ensure that your private Ethereum network is designed to meet its purpose, whether for testing, development, or production environments. Ethereum transactions register Ether transfers or smart contract interactions. Each transaction's record inside a block follows a specific architecture with several key components. The front-end 2 fields specify the sender and destination accounts for the transactions. The 2 field may refer to an EOA account for Ether transfers or a contract address for smart contract interactions. The nonce field is a unique number assigned to the Stellar-owned account, EOA, for each transaction it sends. It ensures that every transaction is processed only once and in the correct order. The gas limits refers to the maximal computation effort allocated for the transactions, while the gas price represents the amount the sender is willing to pay in Ether per gas unit. A higher gas price increases the transaction's priority within the network. The value field specifies the amount of Ether to be transferred from a sender's balance. In the case of a smart contract interaction, it may also represent the amount of Ether required for payable methods. Lastly, the input fields holds additional data. For example, for contract execution, it contains the required parameters, while for contract deployment, it stores the smart contract bytecode. These fields collectively define and facilitate the execution of Ethereum transactions, ensuring secure and efficient operation within the blockchain. Now let's dive into understanding the execution of smart contracts. At the core of Ethereum lies the Ethereum Virtual Machine, or EVM. It is the decentralized computation engine that powers the Ethereum blockchain, providing the environment where the smart contracts are executed. Smart contracts are self-executing pieces of code, written in high-level programming language like Solidity. When deployed on the blockchain, they are compiled into Ethereum bytecode, which the EVM processes and executes. This ensures the contract operates precisely as intended, without any possibility of tampering. Each smart contract is associated with a unique contract account. This account stores the contract's code and also maintains an Ether balance. To interact with smart contracts, EOA's holders use their private keys to sign transactions, and these transactions are sent to the smart contract, calling specific methods or functions and triggering the execution. Now let's understand how Ethereum stores smart contract data using the concept of contract storage. Think of contract storage as an infinite disk drive where data is stored in 32-byte slots, with each slot have a unique address starts from the address 0. These slots are fundamental for management and optimizing how data is saved and accessed in a smart contract. Simple data types like integers and addresses are stored directly in a single 32-byte slot, ensuring efficient use of storage space. However, when it comes to more complex data types like arrays, mappings, or structs, Ethereum employs dynamic storage mechanisms to allocate space across multiple slots. In this Solidity example showed here in the screen, the first slot stores an integer, the second slot holds an address, and the third slot contains a boolean. This is a powerful scheme that allows Ethereum smart contracts to securely handle a wide range of data structures. In order to execute transactions on the EVM, Ethereum uses operation codes commonly known as OpCodes. OpCodes are low-level instructions generated after a smart contract is compiled. These instructions are then processed by the EVM to perform specific tasks. Each opcode requires a certain amount of gas units to execute. For instance, the push1 opcode pushes 1 byte of data into the stack, while the storage opcode stores a value in a contract storage lot. The gas unit cost for these operations changes depending on the action. Storing a new value in storage costs 20,000 gas units, whereas modifying an existing storage is more efficient, requiring just 5,000 gas units. Whether you are transferring Ether between accounts or executing smart contracts, the Ethereum blockchain state is maintained using a complex data structure known as the Patricia-Merkle tree. This is a tree-based system designed to offer both scalability and security by the usage of cryptographic hashes. These hashes form the foundation of Ethereum security, ensuring the integrity of the blockchain and allowing for transaction validation. Through this method, Ethereum can guarantee the authenticity of transactions within each block, offering transparent proof of their execution. Ethereum State is managed through 4 essential types of trees, each serving a critical function. The first one is the global state tree that holds the state of all accounts, including their balance, contract codes, and other data that reflects the current condition of the blockchain network. The transaction tree is responsible for storing all transactions within a given block, ensuring the verification of the integrity of the transactions. The receipts tree keeps track of the receipts of each transaction in the block, providing critical information about whether a transaction was successful and if a smart contract was executed as intended. Finally, the storage tree registers smart contract stored data, so each contract has its own separate storage structure to manage the state. Together, these 4 trees work to preserve Ethereum's integrity, offering a highly efficient and secure way to validate, verify, and prove every transaction on the blockchain. Then the validator node selects transactions from the main pool, normally prioritizing those with higher gas fees. If the transactions involve executing a smart contract, the Ethereum virtual machine processes the contract's logic. In permissioned networks that use key BFT consensus algorithms, validators vote to determine the next block. Once a block is created, it is broadcasted to all nodes in the network. At this point, the blockchain state is updated across the network and the transaction flow is complete. And at this point, we conclude our brief presentation about the core concepts of private Ethereum network. In the next video, we will guide you through the process of creating Ethereum networks using Gobezo, a powerful DevOps blockchain orchestration platform with no-code feature. Thank you for watching. I hope you liked it. And for those who found this content helpful, please consider subscribing to our channel.